Okay, all right, time to get started. Sorry for the late start. So last time we were talking about the chain rule, and just a reminder, a couple different ways to think about the chain rule. One is if you're thinking of derivatives as linear transformations, which really kind of we should. I mean, let me go back to that topic again. Fundamentally, what is a derivative? A derivative is a relationship between input changes and output changes. These changes, be they displacements or velocities, they are vectors. So a derivative is a relationship between an input vector and an output vector. That's what a linear transformation is, right? I mean, it's really very natural to think of derivatives as linear transformations. Anyway, from that point of view, when you compose functions, you also compose their derivative transformations, and pretty natural picture. Pretty natural way to think about it. I mean, whatever action you take to get that vector to turn into that vector, you follow that by, whatever action you take to turn that second vector into that third vector. You're composing the action on these vectors. So very plausible, I think, ultimately. But from a computational point of view, how do we actually get stuff done, right, in practice? Well, we represent linear transformations with matrices, and composition turns into matrix multiplication. So the little bit more sort of day in and day out point of view on the chain rule is that it is that the Jacobian matrix of a composition is the product of the individual Jacobian matrices. Okay. Let me give him just a little bit more slack there. He always likes to go to where there's no more slack. There we go. Okay. Yeah, he likes to sort of set himself up to have a little tension. I don't know why. Okay. So, now, we did an example of this last time. I want to give you a different point of view on it. Now, what I have written down here is the chain rule. This is the derivative of a composition, and you'll notice it's the product of the individual derivatives, and at which point you say, whoa, slow down, where did all this stuff come from, right? So the premise here is that we are viewing a composition of functions like this, where first we have a bunch of variables x1 through xn, and then they go into some function and outcome y1 through ym, and then to the next function and outcome z1 through zp. Right, and then so here's how these Jacobians fit together. The composition views the z's as functions of the x's, and those partial derivatives you note are here. Right, so there's the Jacobian of the composition. The individual Jacobians, well, first, viewing the y's as functions of the x's, here are those partial derivatives, that Jacobian, the air quotes first Jacobian. And then next, the z's as functions of the y's, there's that second Jacobian. Okay, so really, in this setup, what we have here is this is just that formula on the previous page that Jacobians multiply. All right, now what I want to do with this is I want to sort of pull one little thin bit out of this enormous product, this great big enormous product. By the way, there's arguably more information in this formula than it even sort of appears, because keep in mind this is a matrix multiplication, and so that means that each one of these individual elements in this matrix, each one of those is an entire dot product of a row of this matrix with a column of that matrix. So there's a tremendous amount of information there on a page. So what I'd like to do is focus our attention on a single one of the elements in here. Doesn't really matter much which one we pick. No particular reason. Let's compute that one, just to have something to sort of, to write on the page there. Let's think about how would we compute that particular element. as per this matrix product? Well, it's this row, the corresponding row of the left matrix, dot this column, that is the corresponding column of the right matrix. That's the rule, right? That's how we multiply matrices. And if I were to take those elements and let's just actually write down that dot product, here it is, that element that we're looking at. These numbers I have highlighted in blue, the partials of ZP with respect to Y1 through YM, are there and there. These numbers over here, these numbers highlighted in yellow, the partials of Y1 through YM with respect to X1 are there. And notice all I've done in writing this down is write out that dot product concerning this one element of this Jacobian product. Okay. All right. So that's where this rule comes from, and this is a different point of view on the chain rule. There's something a little bit more compact about this version of the chain rule. In a sense, depends on how you look at it, right? This is, in fact, just one equation. This is an overwhelming amount of information, right? And this rule that you have here applies, and one at a time will tell you individually all the elements of that product Jacobian, composition Jacobian. So which one of these is better kind of comes down to, well, what are you really interested in? If you need to understand the whole Jacobian of the composition, this is really nice. The matrix product does all the bookkeeping for you. It keeps track of what goes where and eventually gets multiplied by what. He has an itch in his ear and he's groaning. But if you don't need to know the whole Jacobian, if all you need is to know, there's a particular output variable that I'm interested in, and I just need to know its partial with respect to a particular input variable. That's all I want, is this one element. Then you don't need this whole great big mess. This one succinct little formula answers the question for you. All right. So I want to spend a little time talking about this formula. I want to give you a point of view on how to think about it. This following point of view is an alternative, you might say, to composing derivative transformations. This is, instead of a vector point of view on the chain rule, you might call this a individual variables point of view on the chain rule. And here's the idea. Again, if we're interested just in how this one output variable changes as I change this one input variable. If I'm interested in that one partial derivative, I don't really care what all the other the various other z variables are doing. Partials with respect to xj, so all the other x variables are being held constant. This is really the only part of the picture I need to focus on. And here's the idea. When I change xj, I want to keep track of how this changes. Okay, let me say that a little bit differently. When I change xj, the first thing that's going to happen is all of these y variables are going to change by some amounts. We'll talk about the details in a moment, but you change any one input variables, all these y's are, among other things, functions of that xj that we're going to wiggle. So they're all going to change by some certain amount. Okay, well now let's look at this from zi's point of view. Zi is a function of all these y variables. Each one of them, as it changes, will contribute to some amount of change of zi. Right? If you change y1, that's going to make zi change a little bit. If after that you change y2, well then zi is going to change a little more, etc. All the way on down the line. So, altogether then, the way I'd like to propose we think about this is let's look at the individual paths through which changes can propagate. So, for example, let's look at that path. One way, among others, that xj can cause a change in zi is that by when you change xj, you will change y1, and when you change y1, that's going to make a contribution to a change in zi. Right? that's not the only path through which change can propagate. There is also the Y2 path. So when you make that change to xj that causes y1 to change, which causes zi to change, at the same time, there's also going to be a little propagation, a little wave, what have you. As xj changes, y2 will change, and that y2 also will contribute to a change in zi. So what we really need to do is look at all these different paths through which changes can propagate, and try to understand, each one of them. So we're almost there, by the way. Let's look at these paths that I have highlighted here one at a time. Don't forget, derivatives are factors. So if I want to talk about how much change propagates through this yellow path, what I want to know is what's the factor that I multiply by the input change to get the output change. So however much xj changes, what factor do I multiply to get the contribution to the zi change? And I make I think a very plausible appeal that the total factor is, there's a factor that tells you how much y1 changes per xj change. And then subsequent to that factor, there is a follow-up factor, namely per y1 change, how much is the zi change. So this yellow path is a product of two factors. And that product of two factors you can see right here. And looking at this first term, we have first the factor that says partial of y1 with respect to xj. That says when xj changes a little bit, how much does that cause y1 to change? That's that first factor. And what do I multiply by that first factor? I multiply, per y1 change, how much does zi change? And that's the second factor, partial zi with respect to y1. We're on board. Okay, but did you wrap yourself up? Why don't you just lie down, bud? Second path through y2, same argument. You get this term. Partial of y2 with respect to xj gives you the factor on the first part of this orange path. Partial of zi with respect to y2 tells you the second factor along that path. Okay. And then, et cetera, et cetera. Finally, this last term represents the factor corresponding to that last path. Okay. So there's two different ways you can think of this. Where does this formula come from? You can think of this as being kind of a slice out of the Jacobian version of the chain rule, or you can think of this formula here as representing just the sum of the different propagations of changes that go from xj to zi that I'm interested in. And this propagation of changes through what I like to call intermediate variables is very handy. Day in and day out, very often we need to look at a picture where there's a bunch of variables that are related by dependencies of, this is a function of that, and just being able to look at the paths is very often the most direct and convenient way to think about how the chain rule works. Okay, so let me pause for a second. Does anybody have any questions about this? Everybody happy? Okay. Alrighty. Okay, so here's a quick example. Now, in the last thing we did last time was we talked about how you can compute this. In this previous example we were talking about, you can compute the partial of G3 with respect to x1 by viewing it as being, the appropriate element of that product Jacobian, right? But in order to get that, we had to have both Jacobians and multiply out the whole matrices, and there's a fair amount of arithmetic in that, most of which was irrelevant to this, part of the problem. The fact that this number up here ends up being -1, so what? Right? That doesn't affect this. So let's take instead then this intermediate variables point of view, and So we have here, again, we want to know the partial of G3 with respect to X1. Well, between G3 and X1, there are several intermediate variables. The intermediate variables in there are, I guess I've already erased my little road map, but the three variables here that are sort of in between. Right. So I need to know, said differently, well, let me just come down here. I need to know the partials of G3 with respect to all of its input variables, Y1, Y2, and Y3, each one of which in succession will be multiplied by a different partial derivative, that is, partials with respect to X1, that I'm ultimately taking the partial with respect to, partials of those intermediate variables, Y1, Y2, and Y3. So what we have here is, we have here the three different paths through which change can propagate. That represents, you might say, the Y1 path through which change can propagate, and then this represents the Y2 path through which change can propagate, and this, represents the Y3 path through which change can propagate. Those three intermediate variables, each one gives rise to a term. How are we doing? Everybody on board? Okay. All right. Having written this down, I can just pull individually these elements here. Each one of these is an element out of the appropriate Jacobian matrix. You just pull them right out of the matrices that we were given. They are those, and note we get our same answer that we got previously. Much less arithmetic. Everybody happy? Okay, do be aware of one concern. There is a little, shortcut, cheat, math crime, whatever you want to call it, that students very often like to do in thinking about the single variable chain rule, and that is to just go like that, and that's why dz dx is that product, because the dy is canceled. And there's various complaints that one can make about this, but I don't want to tackle that at the moment. It's not really where we're going. What I want to point out here is that you can't do that when it comes to the multivariable chain rule. You really, really can't. It does not work. And easily seen why. Let's look at this example here. This term by itself, I mean, again, if we're being a little too sloppy about this, there's a temptation to say cancel, and therefore I don't need these terms. Right, which is, well, clearly false. Right? If you take this too literally, that you can just cancel these, you just write down the one term. You would miss two of the three terms, and your answer is dramatically, catastrophically wrong. Does everybody see the problem there? Right, now I'll remind you, there's different ways to say, who's the guilty party, what makes this little illusion, this dangerous little illusion possible. Part of the problem is that we write partial derivatives as fractions. And there's a lot more going on than just, there is this well-defined thing called partial G3. There is a well-defined, separate, independent, standalone object called partial x1, and we're dividing those things. It's just not true. It's more. There's more going on than that, right? For example, notice in this fraction, right, in this partial derivative right here, what's the story here? The story here is that I'm holding most of the x variables constant. I am, however, going to change x1, and as x1 changes, y1 changes. Right? Here's the thing. As I change x1, holding all the other x variables constant, y1 is not the only variable to change. All the other y's are changing too. So this partial y1 says, y1 is changing by some amount, while also all the other y variables are also changing by different amounts. That's not what this y1 says. That y1 says y1 is changing by some amount and all the other y's are fixed constant. So, I mean, there are sort of, I mean, if you look at, the scenarios that describe these two partial derivatives, in those two scenarios, y1 is, there are different assumptions about what's going on with the other variables. Those are not the same thing, and you absolutely cannot just cancel like that. It makes no sense whatsoever. It's a notational illusion, and it's all too easy to sort of fall victim to. So don't step on that landmine. Does anybody have any questions about that? Everybody on board? Okay, I want to talk about confusion of variables. Here is a silly calculation for single variable calculus. As you all know, I like to very often segue into multivariable concepts by revisiting the single variable version of it. Y'all know how to do this kind of thing, I know, but here we go. Here's a couple of single variable functions, x squared and x cubed. What's the derivative of their composition? And let's cheat before we go through the calculation. The cheat would be, well, I can see exactly what the composition is. The composition is x to the 6th. The derivative of x to the 6th is 6x to the 5th. We know that's the right answer. Let's keep that in mind as we go through the calculation. Now, the first thing I'm going to do is fast and sloppy and wrong, just to show you the mistake that students might conceivably make, and that is to say, oh well. We know that the derivative of the composition is the product of the derivatives, and let's see, the derivative of that's 2x, and the derivative of that is 3x squared, and you multiply 2x times 3x squared, and you get 6x cubed. Walk away. And we know that's wrong. Right? Clearly that's wrong. The actual answer is 6x to the 5th. That's wrong. Okay, now it's obviously wrong. What did we do wrong? Well, we were a little too sloppy in writing down the chain rule. We just said g prime times f prime, and we were not paying attention to the fact that g prime has to be evaluated at f of x, not at x. And so, well, really, here's what I'll call a better version of the calculation. Here's our chain rule. And now let's look at this g prime. Notice that what goes into g prime is f of x, right, which is x squared so it's not 3x squared, it's 3x squared squared. That was the oops. That's where we blew it. Okay. All right. So I want to suggest what I think is a better way than this. Rather than remembering, oh yeah, where I see this x, I have to actually plug in f of x. I think there's something intrinsically awkward about the way we've got this set up. Even, in fact, the way the question was stated, there's something really pretty ugly about that. We're given this function f of x. That's fine. It's written as a function of x. Okay, cool. We're given this function g of x. No problem. It's written as a function of x. But fine. Okay, sure. But as soon as they say they want to compose these, we have an issue. If you want to compose and do f first, followed by g, let's write down what the variables are. Let's see here. We have f. Let's see, x is the input variable. Okay, we'll call that x, the input variable. What are we going to call the output variable for f? If I want to have a variable here, you can't call it x. X is the input variable. It doesn't make any sense at all to call the output the same as the input. So let's call that y, let's say. And here's the thing, if what comes out of f is supposed to be the same as what goes into g, that's what composing is. Shouldn't I write g as a function of y? It's pretty weird to say I'm going to write g as a function of this x that's way over here. I'm not plugging x into g, I'm plugging f of x, aka y, into g. So I propose that the very moment that you see that you're composing two functions, you should look at the second one and say, oh, no, I can't leave g as a function of x. That doesn't make any sense. I'm going to have to rewrite g in terms of, let's write it in terms of y. So g of y equals y cubed. Now, that's the same function. I'm just using a different dummy variable to describe the action of g. G is the function that cubes whatever you give me. We're not changing the function at all. Everybody on board? But having written it as g of y equals y cubed, and just to have a name for the output, let's call that output z. Now I have no worry about my confusion of variables. And setting it up like that, look how easy the calculation goes. You can play fast and loose with the chain rule. Derivative of a composition is the product of the derivatives. The individual derivatives, let's see, the derivative of f is 2x, no sweat. The derivative of g, wait a minute, g is now written in terms of y. G of y is y cubed. That means that g prime is 3y squared. And I don't have to remember that, that the g derivative, you're going to remember to plug in a certain thing into that. You don't plug in the regular thing. It's automatic. It says right there, g prime is 3y squared, not 3x squared. That y is the x squared that I need to plug into it. That y is f of x. And so I get the right answer. So my proposal, don't confuse your variables. If you don't confuse your variables, then you'll never step on this landmine and, let's see, this x isn't that. This x needs to actually be f of x. It's a crazy, confusing, ridiculous situation. Just don't confuse your variables. Now, that was all Calc 1. Let's take a multivariable version of this. Here's a couple of functions. Nothing wrong with that as a function. Nothing wrong with that as a function. Perfectly reasonable to write these functions like this, right up until the point where I say I want to find the derivative of the composition. As soon as I say I want to take the derivative of the composition, okay, well look, I can't. This doesn't make any sense. I mean, what comes out of f, that which goes into g, I'm calling that x, which is nonsense, and I'm calling that y, which is also nonsense. So, no good anymore. So let's rewrite, just to avoid the confusion of variables. No big deal. Before I'm getting ahead of myself, look at what would have happened if we had been sloppy about this, if I just wrote product of the Jacobians, right? Just naively write down the Jacobian of g as that. Based on that, I've confused my variables and my answer is wildly wrong. Okay. So let's avoid the problem. I'm going to keep f, no particular reason, written in terms of x's and y's, just as it was given to me. I'm going to name those outputs u and v, and then rewrite g in terms of u and v. So f takes x's and y's and gives me u's and v's. G takes those u's and v's and gives me these outputs that I don't actually have to give a name to, no reason. And now there's no confusion of variables. You can write down the multivariable chain rule, no problem. Here's the multivariable chain rule. Let's see here, the Jacobian of f. We'll start with f. Here's f. Jacobian of f is that. The Jacobian of g. Here's my g. right? Jacobian of G, no problem, and no confusion of variables, because I've written G in terms of new variables U and V. No problem. So now, don't forget you got to plug in appropriately. How do you do that plug in? What are U and V? Well, as I have highlighted in yellow here, the U and the V, the things that go in to G are the things that came out of F. They are x squared plus y squared, x squared minus y squared, as I see there in yellow. And then you can multiply these matrices, and there you go. How we doing? Is everybody happy? Yep.
Doesn't matter if you substitute before or after you multiply the matrices, right?
Does not matter. That's right. Either way is fine. Okie dokie. All right, so this next thing, so I want to talk about second derivatives. Again, I'm going to go back to single variable calculus for a moment. This is arguably a silly exercise, but I think it's easier to kind of see what's going on when there's only one variable. And also, I think there's something comforting about seeing that the things that we're going to do in multivariable calculus, in those instances where this is true, that if it's just a version of something that exists in single variable calculus, there's something kind of tethering about that. I think that's nice. So, okay, single variable chain rule. Our old friend. I'm using Leibniz notation here. And then don't forget we have this little shorthand. This is kind of convenient. But I'm going to say, dy dx. Let's call that y subscript x. That's a notation that we use for partial derivatives in the multivariable context, but it's just to set the stage. I'm going to do that here. Okay. Okay, now suppose I want to take a second derivative. Suppose then I want to take this derivative of z with respect to x, and I want to take another derivative with respect to x. How do I take a derivative of this with respect to x? And now, in practice, in Calc 1 classes, we didn't do this in this, abstract, in generality, because if you want to take a second derivative with the chain rule, take a derivative with the chain rule, and then look and see what you got, and then use the chain rule again. We didn't make a general formula. I want to make a general formula. So, okay, I've got a product. No, fine. I mean, I can take in one of the terms, I'll be taking the derivative of y sub x with respect to x. But in the other term, I'm going to be taking a derivative of z sub y with respect to x. And this is where we have to, wait a minute, what is that? Z sub y doesn't have any, I don't see any x's. Is it a constant? What is that thing, and how do I take its derivative with respect to x? So, I just want to point out that this is something that you can kind of see on this diagram if you edit the diagram appropriately. I make the observation that z is a function of y. So zy says, I'm going to take this function of y, I'm going to take a derivative with respect to y. The result then is a function of y. So let's edit the diagram to reflect that. Zy is a function of y, and here's how I append my diagram accordingly. Zy is a function of y. Let's write it on there. And by the way, yx is likewise a function of x. So when I find myself, as I was up here, I want to take an x derivative of this product, in the process of which I will be taking an x derivative of zy. How do I take an x derivative of zy? The question that we got sort of stumped on previously. X derivative of zy, we're taking a derivative of zy with respect to x, and this diagram helps me understand the answer. The way I do that is by way of the chain rule again. zy is a function of y is a function of x. So this derivative that I'm interested in needs to use the chain rule. Okay. All right, so let's actually do that in practice. Here's our first derivative of z with respect to x, taking now a second x derivative of it. The product rule tells us this. That's just the product rule. I haven't really gotten to the interesting step yet. Quickly before I do that, let me notice that the derivative of yx with respect to x is just yxx. Zy is still zy, no problem. Yx is just yx. The interesting calculation, the derivative of zy with respect to x, this is where we use the chain rule, and the single variable chain rule tells me this. I'm going to take the derivative of zy with respect to y, that's this first part, and then multiply by the derivative of y with respect to x. All right, and then you can rewrite, some more of these things. Derivative of zy with respect to y is just zyy, and notice that dy dx has appeared twice here, as it turns out, and therefore yx squared. Okay, all right. Now, so this is a second derivative chain rule for single variable functions. How come you never saw this in a Calc 1 class? By the way, I never saw this in a Calc 1 class. I never saw this before I started writing this book. Because in practice, this is more trouble than it's worth. Right? This resulting formula is not something that I suggest you memorize. Please don't. It's not a good use of your time. I don't have it memorized. The purpose of this discussion was not to derive this formula. The purpose of this discussion was to show you how you would, if you wanted, for whatever weird reason, to have this formula, what it would be a proper development to get to it. Namely, how do you deal with derivatives of, in the context of the chain rule as applying to second derivatives. And you have to view some of these derivatives as functions themselves of other variables. So I just wanted to kind of set the stage. One thing you might find amusing, if you just kind of want a sanity check, is this a bunch of garbage? Is he making stuff up? Write down a couple of interesting functions of, z is a function of y is a function of x. And just do, compute the left side, sort of brute force, just like you would have in Calc 1. And compute the right side, and confirm. Works. So this is true. You don't have to do that, but if it wouldn't be a hard little sanity check. Okay, so let's consider now the multivariable version of this, and it's morally we're going to take the same approach. Here's a chain rule scenario where I have one function, z is a function of x and y, composed with a different function, x and y are functions of r and theta. I'm going to use the usual polar coordinates formulas for x and y as functions of r and theta. And let's talk about how we compute a second derivative. Well, I'm going to start off by computing a first derivative. Let's start with, how would I compute the partial of z with respect to r? Oh, color crime. Z with respect to r. So here's z, here's r. I have two different paths through which changes can propagate. Changes can propagate through x. Changes can propagate through y. I'm not going to take a Jacobian's point of view on this. It's just a lot more convenient when you only have a couple of variables. And I'm not interested in the whole Jacobian, right? It's just easier to use this intermediate variable's point of view. So there's that, and then we can simplify some of these some of these bits, partial of z with respect to x. Well, I don't know what the z function is, but I do have a shorthand. I'll just call it zx. Likewise, this I will call zy. On the other hand, this partial of x with respect to r, that's something I can compute. That's cosine theta. That's easy. And x as a function of r and theta is given. Easy partial. Likewise for the other one. Okay. All right. So with this, by the way, an analogous argument, you can compute partial of z with respect to theta, which I'll do that one. With the first partial of z with respect to r computed, let's now take the r partial of that. So here we are again, wanting to apply a second derivative in a chain rule context. It's just that now it's multivariable instead of single variable. Well, there's the first partial with respect to r. I just need to take an r partial of this. Let's momentarily think about this process. How would I take an r partial of this thing that I have before me? Sine theta, cosine theta, those are, I know what those are, right? Zx, partial of z. How would I take a partial of zx with respect to r? Is it a function of r? Is it a constant? I don't see any r's in it. Is it a constant? Here we are again. I don't know what the heck this thing is. How does it fit in? How does it relate to the other variables that we're dealing with? Let's get it onto the diagram so we can think straight about how to approach the r partial I will eventually be taking of that thing, cx. Likewise, zy. Okay, so easy argument. If z is a function of x and y, what'll happen if I take this function of x and y, and if I take a partial derivative of it with respect to x? Still a function of x and y. That's the big point here. So that zx is a function of x and y. Because it is a function of x and y, I'm going to indicate thus on our diagram. And so, here's what we started with as our diagram. I'm now appending it to observe that zx is a function of x and y. And likewise, zy is a function of x and y. I'm just documenting. Right? I didn't really do anything there. I'm just making observation of what I've got. Okay. And now we just proceed. So first, here's our first r partial. Now we're going to take a second r partial of it. This is from the previous page. There's two terms. This term, product rule, gives me that. This term, the product rule, gives me that. We haven't gotten to the second part of the chain rule yet. Sort of getting to it. Everybody okay that this is what the product rule says? Right. Now, there's a really nice simplification that you can notice. And that is, let's look at, for example, this. What is the partial of cosine theta with respect to r? Reminder, what does partial with respect to r mean? Partial with respect to r says, all right, I'm going to let r change, but I'm going to force all of the other variables in its world to be constant. So I'm going to hold theta constant, and then as r changes, I want to know how this thing changes. That's what we mean by a partial derivative. Well, wait a second. Cosine theta, if theta is a constant, cosine theta, constant, not changing. So the partial with respect to r of cosine theta is just 0. How do we feel about that? Everybody happy with that? Likewise, partial of sine theta with respect to r, that's also 0. So both of these terms just cancel, and all we're left with then is just these two terms here. Yeah, so these are gone. Okay, and now here's where the chain rule is going to kick in again. Let's look at this one by itself first. In fact, inside of what I have circled in blue, let's look just at that first factor. Partial of zx with respect to r. Well, there's the zx and there's the r, and here, thankfully we have a zx on our diagram now, so I can see I've got a clear picture of what depends on what, and therefore I can infer from the diagram, oh, I need to use the chain rule to compute that thing. Okay. Here, let me make some better choices on how I highlight here. That is about to turn into this. This cosine theta is going to stick around. But let's think about how the chain rule comes in here. How does the chain rule do this? Well, changes can propagate from r to zx by way of x, by way of y. How you doing? Everybody see what happened there? So let's go by way of x. The partial of zx with respect to r. By way of x, we're going to have the partial of zx with respect to x, and then the partial of x with respect to r. So this orange path gives me this orange term of two factors. The red path gives me this red term, again with two factors. Same thing for the second term. The second term partial of zy with respect to r. There's zy, there's r. That's going to turn into all this business. Don't forget the sine theta. It's real easy, by the way. Very common mistake. Students spend so much time thinking about, okay, how do I do the chain rule on this? And they work all this out, and they get all that written down, and they forget to carry over this factor of sine theta. Be really careful. Try to when you write on the page, try to write neatly, if only for your own sort of benefit. And try to group things in a way that makes it visibly clear for you to see what turned into what as I rewrote this equation. Really makes a big difference. And okay, so for this chain rule term here, we have again an x path and a y path, and thus an x term and a y term, like that. Yoke. Everybody on board? Now it's just kind of, dealing with details. So zx partial with respect to x gives me zxx. Partial of x with respect to r is cosine theta, etc., etc. A bunch of little details as you go down the road there. And altogether, it simplifies down to this. Okay. So, real quick, one of the places that this is very, very useful is in physics. A lot of y'all are engineers. But anyway, physics and engineering not that terribly different. There's a lot that you can do with physics that involves derivatives. In fact, second derivatives. So if you want to understand how waves propagate, if you want to understand how heat moves around, through conduction, heat. If I have a heater over here in this side of the room, it's going to be warm on this where I am before it's warm over there. But eventually, the whole room will be warm. Well, how do you quantify how the heat sort of flowed around the room? It involves second derivatives, as it turns out. So those second derivatives are often written in rectangular coordinates, right? But very often it's more convenient instead to deal with those in terms of spherical coordinates because, well, there's a lot of spherical symmetries in the world, right? For example, if you have a hot thing, the heat's going to propagate sort of outward in a spherically symmetric way. So it can be a lot easier to understand these second derivatives in one coordinate system versus another. This absolutely happens, and you're going to notice this as you go through these calculations. So being able to convert second derivatives from one coordinate system to another, very big deal in physics and in engineering. And notice that's what we just did here. We just converted a kind of a second derivative with respect to a polar coordinate into second derivatives with respect to rectangular coordinates. Okay. All right. Okay. So moving along. Implicit differentiation. I'm going to try to be fast with this. I always try to be fast with this section, and it always takes me longer than I wish it would. So I think a lot of y'all have seen implicit differentiation before, right? So kind of a standard topic in Calc 1. There is something sloppy, though, about how it gets treated, and I want to clean up some of the sloppiness of how that gets treated. And then we're going to talk about how to extend that to a multivariable context. So here's a question that we might face, and that gets addressed in Calc 1 classes, and that is here's a curve for which we have an equation. Squared plus y squared is, let's say, 25. And at that point, 3, 4, there's a tangent line. Let's find the slope of that tangent line. And a superficial, mistaken point of view would be to say, oh, slope of a tangent line, let's just take the derivative. Well, derivative of what? Right? We don't have algebra that tells us that what this is a graph of. We have algebra that tells us that we're looking at a level set of a certain function, but we are not currently looking at this curve as being a graph of a function. And derivatives gives you slopes of graphs. That's the level set, not a graph. Everybody see the problem? Okay. So here, worse than that is the fact that this not only is not being viewed as a graph, it cannot be viewed as a graph. This fails the vertical line test. So that's a problem. Right? Now we can clean that up pretty straightforwardly by saying, okay, sure, let's erase all of the curve except for this one little bit of curve. And then so now if ignoring all but that one little piece of curve, now it passes the vertical line test. And so this little piece of curve by itself is the graph of some function. So let's proceed with that. Okay. Okay. By the way, I did just commit a little bit of a math crime, and I'm going to come back and clean that up later. But anyway, let's for the moment, let's proceed. So here's the idea. Yes, I know that I have x squared plus y squared is 25, but I am now choosing to view this curve as being a graph. I want to say, these heights are functions of x. I don't know what that function is, but I can interpret y as being some function of x, and here's that function. Right? Again, I don't know what it is. By the way, let's just pretend that we don't know how to solve for y here. Right? Of course, we do know how to solve for y here, but the point is let's try to understand a method by which we would deal with this if we couldn't. And if it makes you feel, if it would make you feel any better, I could switch to a different algebra where you can't solve for y. We can make this cubic or something, right? But I don't want to have to go to that algebraic inconvenience. So I'm just going to say we're going to pretend that we cannot solve actually for y. Okay. So, we have a level set that is true. We're going to look, however, at this function. That's not the function I want to take a derivative of. I want to take a derivative of y. What I have circled in purple here is not y. It's this other thing, capital S, you might call it. even though capital F is not what I want to know the derivative of, I'm going to take its derivative anyway for two reasons. For one thing, I know what the answer is going to be. F, being as it is 25, right, is going to have derivative equal to 0. I know what its derivative will be. Secondly, when I take that derivative on the left-hand side, then you can see some chain rule coming in here. The derivative of y is going to show up. So this is a mathematical bank shot. I'm going to do a particular task because on the one hand it's going to be this, on the other hand it's going to be that, and these are the two things I actually want to connect, not the thing I'm actually in fact dealing with. So let's proceed. How do we take the derivative there? Well, derivative of x squared is 2x. The derivative of y squared, careful now, this is a chain rule problem. Y squared is a function of y. Y is a function of x. The derivative involves the chain rule. The derivative of the squaring function is 2 times y. Then moving to the inside, the derivative of the inside function is y prime. And then it's all downhill from there. This is the thing that we're actually interested in. There's that y prime that I want to know. So move things around as needed to solve for that y prime. And, little detail. What is this y of x? Y of x is, at the point that I'm interested in, x is 3. And the value of y there, it's 4, because we can see that from the fact that the y coordinate at that point is 4. So y of 3 is 4. So there's your answer, -3/4. Okay, now in practice, here's what y'all wrote down in Calc 1 classes. And that's fine for a Calc 1 context. But I wanted to expand this out just to make sure you see what's really going on. It's very important to recognize that in some places we're looking at a level set of a function. In some places we're reinterpreting as a graph of a different function. And it's important to realize the differences in those functions. Okay. All right. Now it remains, I committed a little math crime. Right, that I need to now go back and clean up. So when I drew this picture here, I was trying to deal with the fact that I had a problem with the vertical line test. This was not a function. So I said, we're going to erase most of the curve. We're going to look only at this part of the curve. And, near the point that I'm interested in, if I look at an appropriately small little piece of curve, then that resulting little piece of curve is a function of x and y. At which point, a valid objection would be, how do you know that? Says who? Right? Just because you erase a bunch of the curve, just because you remove this problem, how do you actually know that this resulting thing actually is a function of x and y? Now, the reason I know is because I know what circles look like, right? But that's a peculiarity. That's every so often you get lucky. You happen to be dealing with a curve that you know about. What if we didn't know about this curve? Right? What if this was a different curve? I just don't know what the shape of it is. Mightn't it be that the point we're looking at, even if you only look at a little teeny little piece of curve around it, it still might not be a function of x and still might not be a graph of a function of x. And I point to this picture as an example. Even on our circle, if you look at that point right there, I don't care how much curve you erase. You take the smallest, teeniest little bit of curve that allows, you've got to have a little bit of curve on either side now in order to build a well-defined tangent line. If there's a little bit of curve on either side, you're going to fail the vertical line test. And to this point, no matter how much curve you erase, it is never the graph of a function at all. And this is catastrophic to the argument we were making up here. The very first step that we made in the argument was, yeah, well, this is some sort of a function. Right? So again, if that's not true, everything that follows is meaningless garbage. It's just garbage. It's not true. This is bad. Everybody see the problem? Okay. So single variable calculus classes don't talk about this hardly ever. But there is a way to address this. Roughly speaking, and now I'm going to switch to a curve where we don't have any actual intuition. This is not a garden variety, circle, ellipse, parabola, something we know about. This is some random wacky curve, and we have to confess that there are some points where no matter how little curve you look at, you're going to fail the vertical line test. On the other hand, there are plenty of points where, like that, if you look at an appropriately small little piece of curve, it passes the vertical line test just fine and dandy. And we need to figure out how to tell the difference between points like this that are a problem versus points like this that are fine. Right? And at points like this, as long as locally, as long as look in some sense nearby, close enough, then yeah, it's a function of x. Then yeah, go on with your implicit differentiation. It's fine, not a problem at all. We have to know how to identify when that happens. So here's the big idea. I'm not going to prove this rigorously. That's not what Math 212 is about. I want to make an intuitive appeal for a highly plausible point of view on this. Why is it that this point is a problem? It's a problem because at that point, it is exactly at that point that this curve is in the process of wrapping under itself. Geometric appeal. It's because it's wrapping under itself that no matter how little curve you look at, you're going to have a vertical line test problem. How can it be wrapping under itself at exactly that point? Well, it can only be wrapping under itself because the tangent line is vertical. The fact that the tangent line is vertical, and keep in mind we are looking at a level set here. Level set of this function capital F, it was x squared plus y squared in the circle example. Because we're looking at a level set, the gradient then, perpendicular as it is to that tangent line, if the tangent line is vertical, that means that the gradient is horizontal. If the gradient is horizontal, let's not forget what the gradient is. The gradient is partial of f with respect to x, partial of f with respect to y. And let's see, if that's horizontal, that would mean that this is 0. Everybody on board? And so that's a way, this is an algebraic way that you can kind of detect the problem that we're interested in. If you have a problem, if the curve is in fact in the process of wrapping under itself, then the function whose level set you're looking at will have a y partial of 0, assuming everything's differentiable. Now, that's the cynical way to say it. If bad news, then consequences, right? Let's turn that around to an optimistic, a more positive way to say things. Rather than problem means algebraic consequence, let's say instead, hey, if this partial derivative here is not 0, if that's not 0, then this is not happening, and we have no problem. I mean, if we had a problem, this would have to be 0. If it's not 0, no problem. So that's the implicit function theorem. Here, the implicit function theorem says that if you're looking at a level set, looking at a level set, and if the partial with respect to y is not 0, then you have no problem. You can view y as a function of x and go ahead and do implicit differentiation to your heart's content. Right? And here's how we'll use that in an example. So this is now, I'm going to show you here now the sort of the third version. This is the third version of how do you compute the slope of the tangent line to the circle at that point, 3, 4. This is what I'm going to call a good way to do it. This is a Math 212 approved way to solve that problem. Step 1 is to recognize that this function f, the function whose level set sorry, I moved the 25 to the other side. It doesn't really matter. But this is the function that we're setting equal to 0. Right? That function, you can compute the partial with respect to y. At the point in question, 3, 4, we get 8, which is not 0. Right? So we identify the function whose level set we're looking at. Take the appropriate partial with respect to y. Plug in the appropriate point, not 0. That means no problem. It is the graph of a function, so y is a function of x. And now everything is fine. And then look, the second half of the question is just this is the same. This is what you wrote in your Calc 1 classes back in high school or wherever. That's perfectly fine. Just go ahead, no problem. So the entire first half of the question, though, and this is a really important first half of the question, and certainly in this Math 212 context, you've got to establish that y actually is a function of x before you start actually treating it as a function of x. Right? So the first half of this question is that which makes the follow-up computation, which is pretty straightforward, by the way, actually meaningful. And this, like I say, this is a big deal. So I just want you to know, full warning. On a Math 212 exam, this is half the points of the question. Right? So it's really very important for the purpose of what we're doing here to establish that what you're about to start treating as a function actually is. So you got to take this seriously. You got to make sure to understand the implicit function theorem and apply the implicit function theorem. Document that you have applied the implicit function theorem before you reap the benefits. All right, so it's time to take a break. We'll take a 10-minute break and pick up here in a few minutes. See you at 11:20.